You would be forgiven if you were wondering whether all of this stuff about orbitals and quantization and hydrogen atom energy levels was completely made up. However, one of the ways that we can actually measure and show that this theory that we've arrived at actually corresponds to reality is by looking at the spectroscopy that is the interaction of the hydrogen atom with light. So there are two things that can happen when we interact an atom with light. One is that if the atom is starting in its very lowest energy state, which we call the ground state, and it absorbs a photon. So in other words, if a photon of light were to come in here and interact with the atom, what can happen is, because this light has an energy that's related to h times its frequency, that energy can be transferred to the atom. And so the atom picks up this amount of energy. So it's starting here, but now it has more energy. And so it picks up that amount of energy and goes to a higher energy level. So that's called absorption, when we go from a low energy level to a higher energy level. So that's absorption. And that's when the light transfers energy to the atom. If we look at these arrows that are coming down, we're depicting an electron in the hydrogen atom, so the hydrogen atom at a higher energy level, so starting in this energy level, and then dropping down to this lowest energy level. But energy has to be conserved, and so if the atom loses this much energy, so this is the amount of energy that the atom has lost, it has to go someplace. And so if it loses that amount of energy, then it's going to end up as a photon that is emitted by the atom to get rid of that excess energy. So the emitted photon, or the emission of light, is a consequence of the atom getting rid of energy. And that energy is turned into light. So one thing we know is that energy is conserved. So if we start out with some light, some energy with the light, and we have the energy of the atom initially, that amount of energy has to be equal to the amount of energy that we end up with at the end. And at the end of this process, the atom is in some final state, and we don't have a photon anymore or we don't have any light. We call that amount of light a photon. We don't have that photon or that light anymore because the atom has gained that energy, that light. And so we can see from this conservation of energy that this is our initial state of the system. We have light, and this is our final state of the system. And we have light and the atom in some energy level. And then at the end, our final state is that we have the atom in a new energy level, the final energy level. So if we just manipulate this equation and subtract the initial energy of the atom from both sides, we can write that the energy of the light is equal to the energy final of the atom, so F for final, minus the energy initial of the atom, so I for initial. Whenever we have a quantity where we're taking the final value minus the initial value, we write that as delta E. So delta always means change. How has the energy of the atom changed from its final to its initial? And we always do that as final minus initial. Notice that this energy level is smaller energy than this energy level up here. So the energy is increasing in this direction. So if I look at this down arrow, then my final state is smaller than my initial state. So if I take a smaller number and subtract a larger number, this is going to be a negative change in energy. So for emission, we have a negative change in energy of the atom. So the change in energy of the atom is less than 0. But if we're going up and absorbing energy, if the atom is absorbing energy, its final state has a higher energy than its initial state. So larger minus smaller is going to be a positive number. And so for absorption, we have that the change in energy of the atom is always greater than 0. Now this poses a conundrum, a little bit of a problem, because the energy of the light is always positive. So it can't be equal to the change in energy of the atom if that change is negative. So in reality, what we really mean here is that the energy of the photon is the absolute value of the change in energy of the atom. Or we just have to remember that when the atom is emitting light, that we treat that as a negative value. And when the atom is absorbing light, that's a positive value. We can go a bit further here because we know that we can calculate the energy of light by knowing its frequency and Planck's constant. We also know that the energy level for an atom is equal to minus the Rydberg constant divided by n squared. And so we have an n initial and an n final if we're absorbing, or an n initial and an n final if we're emitting. So if we look at just this arrow here from 2 to 1, right, then we can calculate the energy of the n equals 2 level, and we can calculate the energy of the n equals 1 level, and we can subtract those to get the change in energy for the atom. So we could write that this is E final, which is minus the Rydberg constant divided by the final quantum number n squared, minus n initial. And n initial is the Rydberg constant divided by the initial n quantum number squared. And so we could write that. We know that these two things have to be equal because this is the energy of the light, this is the change in energy of the atom. And so I should be able to then factor out a minus r sub h. So if we factor in r sub h out of each of those terms, h nu is equal to minus r sub h. And then we have 1 over n final squared minus 1 over n initial squared. And this is the equation that you will often see for how to calculate the frequency of light that you would expect for any given transition from an initial n level to any final n level. So let's do an example problem using this equation. So let's look at what the energy of a photon emitted is when a hydrogen atom goes from n equals 5 to n equals 2. So we know this is an emission because we're going from an initial state that is higher than a final state. So the atom is losing energy, therefore it's emitting a photon. So if we think about our equation, we have that the energy of the photon, the light, is equal to minus the Rydberg constant times 1 over the final n, so 2 squared, minus 1 over the initial n, which is 5 squared. Okay, so the Rydberg constant is 2.18 times 10 to the minus 18 joules. And so we have 1 over 4 minus 1 over 25. And so if we do that on our calculator, we get minus 2.18 times 10 to the minus 18 joules times a 0.21. And so that gives me an energy for my photon that is minus 4.58 times 10 to the minus 19 joules. Now remember that the photon energy can't be negative, and so I'm going to take the absolute value of this, and so my photon has an energy of 4.58 times 10 to the minus 19 joules. If I wanted to know the frequency, so what would be the frequency of that photon? Remember that the energy is equal to Planck's constant times the frequency. And so if I want the frequency, I just have to divide both sides by Planck's constant. And so I take this energy, 4.58 times 10 to the minus 19 joules, and divide by 6.626 times 10 to the minus 34 joules times seconds. And you'll see that my joules divide out, and I'm left with units of per second, which is a good unit for frequency, so that seems to be right. So if I take this energy and I divide by 6.626 e to the 34 minus, I get a frequency of 6.91 times 10 to the 14th per second, or that per second unit can also be designated as a hertz. If I wanted to know the wavelength of light, remember that frequency times wavelength is equal to the speed of light. So if I want to know the wavelength, I divide both sides by the frequency, and that will tell me that the wavelength is the speed of light divided by the frequency. So if I take the speed of light, 3 e to the 8th, and divide by my 6.91 e to the 14th, I get a wavelength, so 3 times 10 to the 8th meters per second, divided by 6.91 times 10 to the 14th per second. So my per seconds divide out, and I get it in terms of meters, and that number is 4.34 times 10 to the minus 7 meters. If I want to convert that to nanometers, I can remember that 1 nanometer is 10 to the minus 9 meters. So those two things are equivalent, and so I can use that as a conversion factor. And when I do that, my meters will divide out, and I'll be in nanometers. So 10 to the minus 7 divided by 10 to the minus 9 is 10 squared. And so I end up with 434 nanometers as a wavelength for the photon that gets emitted when I go from n equals 5 to n equals 2. So you can see that once I've calculated the energy, I can use my relationship between energy and frequency to get the frequency. And once I have the frequency, I can use my relationship between wavelength and frequency to get the wavelength of light that would be emitted. Let's do another example. So in this example, I know what level my hydrogen atom ends up in. So I know that N final is equal to 2. And I know the wavelength of the photon that is emitted when my hydrogen atom makes that transition. So I'm going to convert this to meters. And then what I want to know is what level did I start in? And so we can use our same process. Remember that our equation tells us that the energy of light that is emitted is equal to minus R sub h, 1 over n final squared minus 1 over n initial squared. And so I need the energy of the light, but I have the wavelength of the light. So I can use the wavelength to find the frequency. So wavelength times frequency equals the speed of light. And if I want the frequency, I just divide both sides by the wavelength. So that gives me frequency equals the speed of light divided by the wavelength. So 3 times 10 to the 8th meters per second divided by 656.3 times 10 to the minus 9 meters will give me my frequency. So 3e to the 8th divided by 656.3 e to the 9 minus. And so my frequency is 4.57 times 10 to the 14th hertz or per second. Notice that my meters have divided out and I have units of per second, and a per second is a hertz. So now I have my frequency, and I can use the frequency to find the energy. So the energy is Planck's constant times the frequency. So 0.626 times 10 to the minus 34 joules times seconds times my frequency, 4.57 times 10 to the 14th per second, and that gives me 3.029 times 10 to the minus 19th joules is the energy of light that has been emitted. So that is the energy of light that's been emitted. And I know that my final N is 2, so that's 2 squared equals 4. And I know my Rydberg constant. So now I just need to solve for N initial. Now here's the problem though. When I'm emitting light, that energy of the light is given off. And so I have to make that negative first. So I have to say 3 minus 3.029 times 10 to the minus 19th joules is equal to minus 2.18 times 10 to the minus 18 joules times 1 over 4 minus 1 over n initial squared. And it's the n initial squared that I'm solving for. What I'm going to do first is to multiply through by minus 1. So if I multiply through by minus 1, I can cancel out my minus signs. Now I'm going to divide both sides by 2.18 times 10 to the minus 18 joules. So I'm going to get rid of the 2.18 times 10 to the minus 18 joules, the Rydberg constant, on my right-hand side. So when I do that, I end up with 0.1389 is equal to 1/4 minus 1 over n initial squared. So now I can subtract 1/4 from both sides. So that's going to give me 0.1389 minus 0.24 because 1/4 is 0.25 is equal to minus 1 over n initial squared. So when I subtract 0.25, I end up with minus 0.1111, okay, is equal to minus 1 over n initial squared. So now again, I can multiply through by -1 to get rid of my minus signs. Now what I want to do is I need to flip this over because I don't want 1 over n squared. I want n, right? So I need to flip this over. So that means I have to flip both sides over. So 1 divided by 0.111 equals n initial squared. So 1 over this number is equal to 9. So 9 is equal to n initial squared. And then I take the square root of both sides. And when I take the square root of n initial squared, I get n initial, and the square root of 9 is 3, and so n initial is 3. So in order to emit a photon of 656.3 nanometers, I have to start in n equals 3 and end up in n equals 2.